today. This is Professor Carlos Torres-Verdin, broadcasting live from the beautiful hill country of Texas for Principles of Formation Evaluation PGE358 Spring 2020. Today we are going to have an excellent practical applied lecture having to do with dominant mineral composition of rocks. Here we have a carbonate rock, and it has porosity, it has solid composition, and the interesting thing is that to quantify the porosity of this rock, which we need for quantifying the storage and flow properties of it, we need to quantify the solid composition of the rock. That's a very important component of the estimation of porosity. To do that, we are going to make use of the physics principles behind the acquisition of density, photoelectric factor, and neutron borehole measurements. We're going to look at the phases of the measurements. We're going to look at the engineering of the measurements. We are going to look at the environmental corrections for the measurements. And we are going to look at the interpretation principles. And to do the interpretation principles, we are going to analyze a few examples of well logs taken from the compendium. We are going to use the interpretation charts that combine density and PEF for electric factor and density and neutron porosity to analyze the porosity, the effect of the dominant composition, to diagnose it, analyze it, and to also understand the effect that fluids lighter than water, have on the interpretation. At the end, I'm going to talk about how photoelectric factor measurements can be used to assess dominant clay mineral composition. That's a continuation of spectral gamma ray logs. The lecture has two parts. The first part goes through the principles of density, photoelectric factor, and neutron logs. That's the first part. I suggest that you take a break when you finish that. Take it easy, take a snack, relax, and come back subsequently for the analysis of the examples. It's a long lecture, but it's a very interesting lecture, so you have to take it one step at a time. I hope you enjoy it. I hope you like it. Stay healthy, be happy. Let's go for it.
Hello everybody, here we are with a new exciting presentation on the principles of how to diagnose, quantify dominant mineral composition in rocks. So today I'm going to introduce a method that is typically used by the industry to assess dominant mineral composition based on density, photoelectric factor, and neutron logs. I will describe the physics and the engineering elements of those measurements, their limitations, and their environmental corrections before we interpret them. We are going to have several exercises, demonstrations of how the interpretation cross-plots between PEF density and neutron density are used to assess dominant mineral composition, and then we're going to use the remaining part of the presentation to talk about other methods that are normally used for the same process in more complex conditions. So here we go. Fasten your seatbelts. Let's do it. Please note that what I'm going to talk about here is contained in the PowerPoint presentations that are titled Density Logs, Neutron Logs. I'm also going to make use of the compendium, part 2, pages 1 to 3, 13 to 15, and 18. All of them well logs in the large format. And I'm going to use 5 of the Schlumberger interpretation charts. The idea is for us to become competent at using these interpretation charts. And for that, we're going to have examples. I also want to remind you that the textbook, chapters 6 and 9, is a great source of additional information in case you want to expand the topics that I'm going to cover here today. Now, why is it so important to determine matrix composition, the solid composition of a rock? Well, because you need it to estimate porosity. You need the density of the matrix to estimate porosity. Second, many of the calculations that we do in geomechanics, elastic properties, all of them are based on elastic properties of the solid composition. So knowing the solid composition will give us a very important entry to those calculations and interpretations. There are also fluid matrix interactions that have to do with the mineral composition. Well stimulation, for instance, acidizing, is based a great deal on knowing the mineral composition of the rock. So there are several principles, several applications that do require that we know the solid composition very well. But let me remind you, this is the formula that we use for linking the density of the rock, which is the measurement. That's what we measure. The measurement that we get from the density tool is the bulk density, grams per cubic centimeter. Our task is to get to porosity. But to get there, we need to know both the density of the matrix and the density of the fluid. The density of the fluid oscillates between 0 and 1, whereas the density of the matrix can oscillate between values 1.5 all the way to 3.5 or so. So it has a wider range of variability. And this is, of course, a linear relationship that we have here. And the transformation that gives us back to the porosity is also a linear transformation that requires those two entries. So it's very important to remember that to get there, we need to know the density of the matrix. Of course, we also need the density of the fluid. And the density of the fluid is obtained or inferred by the combination of density logs with neutron logs. There are two unknowns, one data point, actually three unknowns, porosity, density of the matrix, and density of the fluid, and one known, which is the measurement, the bulk density. So we need to use additional information to be able to estimate porosity. That is to say, independently we need to get the density of the matrix, and independently we need to get the density of the fluid. We can only achieve this by combining multiple other data sets. In this example, in this presentation, I'm going to show you how to use the density log, the photoelectric factor log, and the neutron log. In some instances, when the composition is very complex, and we also have to resort to other measurements, such as the sonic log, or even we need to support interpretation with core data, mud logs, a number of things that I'm going to talk about in due course. So, very important. Remember, we need to obtain in some way the density of the matrix. And this is a Porse scale photograph of a rock. And what I want to point out is, yes, there are some rocks that have very, very homogeneous grain composition, maybe in the clastic domain when you have siliciclastic rocks. But there are many other rocks that do not have the same composition, or the grains do not have uniform composition. This can happen in very complex rocks. Carbonates are one example of that. So it's important. And also, please bear in mind that we don't expect to have the same grain composition everywhere in depth. So depth by depth or formation by formation, we have to take all of these into account. And here's another beautiful photograph of classic rocks made of different composition. Here's a classic rock from Austin made of carbonate rocks. Here is a photograph from Iceland, where the grains are made of volcanic material. Here is a sandstone from Italy, where the grains have an extremely variable composition that includes iron. And here is a sandstone whose grains have microporosity, and the composition of the grains, the main ingredient of the grains, is a shell. So we can have variable grain composition constituting clastic rocks. When you look at the pore scale of the rock, we can also see significant variations. Here is a sandstone where we have the pore, the grain, mostly quartz. Then we have calcite cement. These can happen, rocks, clastic rocks that are cemented with calcite. Then we have the pore space, which is an important thing for storage and flow. And we can also have clay minerals, such as kaolinite in this case. So even at the pore scale level, we can see significant variations in the grain composition. Of course, we need to understand which one dominates here. In the carbonate world, things are even more complex, because in carbonates we cannot assume that the same pore fabric, the pore shape, the pore constitution will remain the same with depth. We have very significant variations at the outcrop scale, shown here, and also at the texture visual scale here, where we have holes made of imprints of fossils. And here we also, at the thin section scale, we also see strong variations of the constitution of the rock because of the way the rock was made. So one of the things that we often find in carbonates is that their composition is extremely variable with depth. So almost depth by depth, we have to quantify the dominant mineral composition, so that in turn we can quantify depth by depth the porosity of the rock, which is not necessarily as drastic as in the case of clastic rocks, where even though the grain composition cannot be assumed to be constant, we don't necessarily see very strong variations of the grain composition over short distances in depth. Now, when you go to outcrops, you also see that rocks can be very complex, because if you drill, for instance, a well somewhere here, the well is going to penetrate clastic rocks and also carbonate rocks, and the carbonate or clastic rocks are going to have different bedding planes, different constitutions. So it's very important to, when we go and measure the well logs across those wells, that we have a way to first of all, signal those variations, detect those variations. And second of all, have enough information and measurements to be able to calculate the storage and flow properties of the rocks, which require the knowledge of the matrix density. Or for other things such as geomechanics, it might be necessary to understand the solid composition in great detail. This is the case of the Eagle Ford Formation, where many horizontal wells are drilled and the many fractures are implemented, and the fracture implementation relies heavily on understanding the mechanical properties of the rock, which in turn depend a lot on knowing the solid composition. In this case, the main solid composition of the Eagle Ford is calcite or dolomite, and then we have the Buda Formation just below, which is a mostly calcareous formation. Now, in the well logging world, where we have a multitude of logs, gamma ray resistivities are phase and attenuation resistivity for LWD, and then we have for electric factor, a log that I'm going to introduce today, neutron density. And what we typically do with these combinations of logs or more is that we prepare this extraordinary interesting diagram that gives us a cross-section of the volumetric concentration of the rock at a given depth. And here you can see what fraction pertains to porosity fluids, what fraction pertains to limestone, what fraction pertains to sandstone, and what fraction pertains to silt. So depth by depth we do this analysis because the proportions and fractions are very important. So that is what constitutes the volumetric concentrations of the rock, be it the fluid composition, porosity, and within the porosity the various fluids, and the solid composition, which can be constituted by a number of minerals. We can have many minerals. In fact, sometimes people even lump the clay minerals in here, so that makes a composition of several elements. But in this presentation, I'm going to focus our attention on the cases where we have at most two minerals as part of the solid composition of the rock. Here's another interesting plot where, in addition to showing the estimated composition of the rock, solid composition, we can have in this example, which is a barnett well, we can have in this example clay minerals. We can have also calcite. We also have quartz and pyrite. All of these are represented here in their proportions. That's what this colorful diagram does. And to support those calculations, here we have X-ray diffraction tomography data, which is you take samples of the rock and you send them to the laboratory, and which using X-ray diffraction analysis, those compositions can also be estimated by that procedure in the laboratory, and they serve as ground truth to compare to the estimations that we perform with well logs. In addition to that, we also have core measurements of porosity and core measurements of water saturation and total organic carbon, porosity, and water saturation. And like that, we can also have core measurements of proportions of minerals to support the estimation. All of these needs to be done from well logs so we understand the composition of the rock depth by depth. Here's another example, also the barnett shell, in which we have various forms of logs, well logs, gamma ray, resistivity, density, neutron, photoelectric factor. Then we have porosity and core porosity. We have also water saturation and core water saturation, presence of kerogen, how much that's the volumetric concentration. We also have X-ray diffraction tomography data from the core measurements, and then we have estimations of volumetric concentrations, which in this case we have quartz, carbonate, clay, pyrite, and hydrite. All of these were estimated from a well log that uses spectroscopy based on neutron capture gamma ray emissions. And here is the estimation obtained from the conventional well logs to be analyzed and supported compared to those other estimations. So it's important because here we have variability of the proportions of quartz and feldspar and the proportion of carbonates. And that's, as I said, important for a number of reasons, geomechanical reasons for estimating the effective grain density or solid density, and also for development of hydrofractures, a number of things that can be applied for this. Here's another example where we have a substantial amount of core data. We have a number of logs, neutron density, resistivity logs, and then we have also core data of matrix density. So it turns out that whole core is used to take plugs, and the plugs are sent, or small sections of the core are sent to the laboratory, and then the grain density is measured. And here is a validation of the grain density measured in the laboratory with that estimated with well logs. And here is total porosity estimated, core data, and continuous line is the estimated from well logs. Similarly with water saturation, fluid density, and finally we have this beautiful colorful diagram that is the estimation of the concentrations of illite, quartz, limestone, dolomite, water, and gas. So this part that you see here is the porosity part, and the porosity part is also partitioned into water fraction and gas fraction. All of these, this beautiful colorful diagram is estimated from well logs supported by core data. So that's the analysis that typically is done with well logs around the world, and these compositions are compared across many wells, and analyses are made based on those compositions. I also have to remind you that mud logs, these logs that come from the drilling process and from the recovering of drilling cuts, are analyzed, and the analysis of those cuttings, in addition to all drilling parameters, also yields proportions or volumetric concentrations of materials. In this case, for instance, we have descriptions that include salt, calcite, and hydrite, limestone, and so forth. So on here, for instance, we have shale, we have sandstone, we have dolomite, a number of things. In addition to all of that, of course, we also have an analysis, chromatographic analysis of the fluids that come from the borehole, but that's a different story that we can talk later. But suffices to say that mud logs are very important because even though they're not as precise as borehole measurements, they do give us ground truth to analyze the concentrations that are subsequently estimated from well logs supported by core data. So today's lecture, I'm going to talk about only dominant minerals. We can estimate many minerals if we have the right number of measurements, but today I'm going to talk about estimation that is supported by density, photoelectric factor, and neutron logs. Of course, the analysis has to support the resistivity logs, the presence of invasion, and so forth, so on. I'm going to avoid any mention of shale clay minerals because they can be very complex, and there are techniques to take them into account, but I'm not going to take them. So we're going to focus our attention on sections where we can rest assured that the presence of clay or shale is negligible. We are going to make emphasis on the fact that some of these tools are extremely sensitive to rapid caliper variations with depth, so we have to take control of them. And in the analysis, in the interpretation, we also know that if there is barite in the mud, therefore in the mud cake, so the measurements can be affected by that, and we have to have a ground truth for the measurement reliability in presence of barite. We are going to make the assumption that when we go to the interpretation, that all of the measurements have been corrected for borehole environmental conditions. Those conditions I'm going to describe what they are. And also in the estimation of these properties, it's important that we don't neglect the presence of fluids lighter than water. We are going to use cross plots between density and photoelectric capture cross-section, which is called photoelectric factor measurements, and also cross plots of density and neutron measurements. And last but not least, at the very end of the presentation, I'm going to show the procedure that is typically used to combine PEF, photoelectric factor logs, and spectral gamma ray logs to identify dominant clay mineral composition in shales or other rocks. So here is the cross plot that will be the subject of our analysis. Every single logging company has a version of this plot. I'm showing you the one for Schlumberger, where in the x-axis we have photoelectric factor, and in the y-axis we have bolt density. I'm going to mention this later, but that's one of the charts, interpretation charts, that we're going to describe in great detail. We have several examples. Similarly, the chart that we have used before to make conversions of neutron porosity from one matrix, let's say sandstone, into limestone, vice versa, or dolomite. We have used that before, but now we're going to use it in the context of understanding what is the dominant mineral composition of a given rock when we have neutron and density measurement. So here is the version of the plot by Schlumberger for one of their Neutron tools. And last but not least, here we have the cross plots that I'm also going to talk about at the end of the lecture, which they are used to combine spectral gamma ray logs with photoelectric factor, and the intent is to determine in a more granular way dominant clay minerals present in the rock, in the shale. That's what we're going to talk about. So those three important charts. Now, with that said, let me give you a very, very, very short introduction about the wireline density photoelectric factor tools. I'm going to be doing the same thing for the Neutron tools. Now, I want you to understand this presentation is not intended for an exhaustive detailed analysis of the instrumentation, the physics principles, the calibration. For that, we would have to have a nuclear physicist here, and there are many good ones. In fact, I want to recommend for you the book by my very good friend Darwin Ellis. Darwin and I used to work for Schlumberger Doll Research. He's a great friend of mine. Now he owns a bookstore in Richfield, Connecticut. I'm not doing an info session for him, but his book has an extremely well detailed chapter on nuclear properties, the engineering behind the well logs, nuclear logs, how they're used for interpretation, and everything else. Darwin Ellis is an excellent person, knows his nuclear physics very well, and you can consult that. Today, I'm going to talk about only the main important principles of these measurements. So let's begin with the wireline and PEF tools. These measurements are extremely, extremely interesting because what we do here is, with this cartoon I want to show you, we have a source. This is a radioactive source. And the radioactive source is naturally emitting gamma rays, photons. Photons have no electric charge and no mass, they're pure energy. But they don't have one single energy, they have different energies depending on the radioactive material that they came from. And also, these gamma rays or photons, when they're sent here in a given number, they go and do their propagation, their movement in the medium. Some of them will eventually make it back to the borehole where we have a sensor. The sensor is going to detect those gamma rays, and by using a scintillator and a photomultiplier similar to what we have in the spectral gamma ray logs. And what happens here is that we have a certain number, concentration of gamma rays that make it out of the cesium, the radioactive source here, and many of them are going to be absorbed, and eventually some of them will make it back to the sensor. The point is that the denser the material is, the lower the count rate that we're going to receive. And this is what this plot is intended to show. We know that these detectors over here are continuously going to be counting how many gamma rays impact them per unit time. That's what we call the count rate, number of gamma rays per unit time. The source is a constant source, or we can assume that it's constant, so it emits the same number of gamma rays regardless of what medium the gamma rays are sent to. And what happens is that the denser the material is, the lower the number of gamma rays that are captured in the sensor. And the lighter the medium is, the higher the number of gamma rays that are captured by the sensor. So you see the count rate, number of gamma rays, when calibrated per unit time, when calibrated properly, can yield some indication of the bulk density. And that is this plot, which says that for a given bulk density, let's say when the rock is very dense, the count rates are very small. Look at the y-axis here is a logarithmic scale, whereas when the bulk density is low, let's say 1.8 grams per cubic centimeter, then the count rate is extremely high. These two plots here are to indicate that these count rates are measured oftentimes not by one sensor, by multiple sensors, as I will explain in due course. Now, let's look at the tool itself. Here is a plot of the tool. For scale, we have a pen, a Longhorn pen right here. And the tool, it has a source, a radioactive source. In this example, we have the radioactive element is cesium-137. The half-life of cesium-137 is approximately 30 years. You don't want an element, a radioactive element, whose half-life is very short, because if you start with a given concentration of that material, when you begin the logging job, then maybe when you finish the concentration will not be the same, and therefore you cannot associate the count rates across the entire well with a particular density because the source is not the same. So we have to make sure that the source during this job has the same properties in 30 years is very good for that. The strength is too curious. The energy of the gamma rays is approximately 0.662 mega electron volts. I'm going to talk about this energy because it's very important to understand this value of energy for the interactions that the gamma rays are going to have with rocks. And there are two sensors, sodium iodide sensors. Those are the sensors that are the scintillators and photomultipliers, but some tools can have up to 3. What happens is that this is the source. This is where the cesium-137 is emitting gamma rays in a collimated way. Then some of them will make it to the near sensor, and some of them will make it to the far sensor. We use two sensors to compensate for several environmental issues, but most notably by the presence of mud cake or standoff. I also want to say that the source, the far sensor, it's hard to appreciate from this plot, but the far sensor, the diameter of the far sensor here is often larger than the near sensor to compensate for the loss of gamma rays as a function of distance. These are very important distances. Please note the separation with this pen, and that gives you an indication of the resolution of the measurement. The source insertion aid, which is here, is used to insert the cesium-137, the pill, behind this location over here. It's a radioactive material, so you have to be trained to do that. This is a pad tool. The pad is this long. The pad is open, retracted with mechanical arm right here. There's also a piece behind the tool that presses the pad toward the borehole wall for maximum contact with the formation. So it's important that the borehole wall be relatively smooth along the complete length of the path. That's a very important principle. And also the retraction arm that we have here to press the tool against the borehole wall is often used to measure the caliper. Now, why do we have two sensors, or maybe 3, but in most cases 2? Well, because very often when we're logging through porous impermeable formations, because the drilling mud has solids, then what happens is that we have this mud cake. And the mud cake, depending on the thickness and depending on the density of the mud cake, when the source is sending the gamma ray toward the formation, some of them might be absorbed by the mud cake before actually they make it to the formation. Also, when they make it back to the sensor, some of them might have to undergo absorption when they go through the mud cake again in their flight to the sensors. So the mud cake presents a significant issue because it has to be taken into account to compensate for the absorption of gamma rays going through it, especially when you have very heavy mud cake. Another measurement that is made here, I'm going to talk about later, is a photoelectric factor log, and that is made with only the near sensor. And here is a plot. This is a Monte Carlo plot of how these gamma rays actually go into the formation. What I'm showing here is a picture of how at a given time, here is the source right here, and how the cesium-137 source sends gamma rays photons, and how the concentration of gamma rays photons eventually makes it back to the sensor, and what is the preference path that they take to get back to the sensor. In this case, for the far sensor, it could be for the short sensor. So this is not like a laser beam that goes from one place to another. Of course, a laser beam is also photons, different energy, but in this case, we have somewhat of a blur laser that goes between the source and the sensors. And not all the gamma rays that come out from the source here are going to make it into the sensor. When we have very dense materials, very few of them will eventually make it to the sensor. When we have very light materials, more of them will make it to the sensor. So this sensor, the sodium iodine sensor, is going to count per unit time how many photons impacted it. Of course, please also remember that that measurement is made at the same time the tool is moving. This is not a stationary measurement, so we also have to take that into account. And there's some elements of probability theory that says that there's a Poisson distribution going on here. So we want to minimize the effect of noise. We have to continuously stack, make many measurements, and take an average of the measurements so that we minimize the effect of noise, the law of large numbers. Now, what is that happens to gamma rays when they're sent to rocks, when the cesium-137 source, radioactive source, is releasing its gamma rays, 0.6 megaelectron volts, into rocks on their way to the sensors? Well, there are three ways in which those gamma rays can interact with rocks. One is Compton scattering, which is the most important one. Second one is the photoelectric factor, and the third one is what we call pair production. This is the least important in our business, and it happens when the energy of the gamma rays emitted by the radioactive source is sufficiently large that the gamma rays interact with the nuclei of the substance. And out of that, you have the generation of a positron and electron pair. And that's the reason why it's called pair production here. But this only happens at energies that are characteristically very high, in fact higher than the energy provided by the cesium-137 source. The second most important one is the Compton scattering. What happens is that when you have a gamma ray with a certain energy, it goes toward a given atom and it doesn't reach the nucleus. It actually interacts with the cloud of electrons. This is something that is very important to remember, that density measurements for the energy range that we deal with here, those energy measurements, those gamma ray measurements interact mostly with the electrons, with the cloud of electrons. So here's a gamma ray coming to an electron, and what happens is that two things happen. The gamma ray is scattered at an angle, but the energy of the scattered gamma ray is lower than the energy of the incident gamma ray, and some of the energy is taken by this fast electron. So the point is that these gamma rays go on and impact multiple atoms, multiple electron clouds, and every time they do it, they are deflected, and they lose energy. So they continue to lose and lose energy. So when their energy is so low, it reaches a threshold, instead of being deflected, we have the so-called photoelectric effect, which is that the gamma ray comes to the cloud of electrons and it's absorbed by an electron. So the gamma ray is gone. The energy that the gamma ray had is absorbed by the electron. The electron moves to a higher orbit, now becomes a fast electron, and that's what generates in solar panels. That's how they collect electrons to produce electricity, and some of these electrons will eventually yield light by going back down to their normal orbit. So here's the thing, we have three types of interactions. There are three possibilities with which a gamma ray, a photon, when sent to rocks, could interact with the rocks. The high energy, which is very uncommon, is per production. We don't even talk about that because it's so negligible. But when it does Compton scattering, that's very important because that's the prime mechanism whereby the gamma rays will begin to lose energy. And finally, they're captured, and they're captured via a photoelectric effect. So essentially, the count rate decreases in dense materials because many of those gamma rays are absorbed in the medium by way of the photoelectric effect. They can continue to live, so to speak, but they lose energy as they undergo Compton scattering interactions. So they lose energy until they're finally absorbed via a photoelectric effect. And the count rates follow an exponential rule, which is the initial count rate will decrease, of gamma rays, will decrease with distance traveled. And the rate of decrease will depend on, this is for the Compton scattering, it will decrease based on the electron density and also the mass attenuation coefficient. So here is an exponential law. Of course, the longer the distance, the more the loss of gamma rays that are captured because of photoelectric factors. So they lose energy, they're captured, so the count rate begins to decrease. And that decrease of count rate is exponential, and the exponent is governed by distance and is also governed by the electron density. So the higher the electron density, the higher the loss of gamma rays. That's what happens in this situation. Now, gamma rays, when they make it to the sodium iodine detector, they will come with different energies here. But in all the cases, the scintillation material will convert the photon into light, into voltage, essentially. The voltage or the light, and the light also will be photomultiplied for amplification inside as the photomultiplier. So we have the scintillator and the photomultiplier, and essentially the energy of the gamma ray as it impacts the scintillator will be recorded as a voltage, and the higher the voltage, the higher the energy. So we have a way to distinguish between the different energies of the gamma rays as they come, and potentially we can differentiate the low energies from the high energies by way of several energy windows. And in fact, the photoelectric factor gamma rays that are recorded in the near sensor are those that are counted as the low energy gamma rays that hit the sodium iodine detector. So there's a separation of count rates for low energy and a separation of count rates for high energy. And here is a plot of how the energy tends to decrease as a function of atomic number, and there's a threshold that has to do with the photoelectric effect. The y-axis is the atomic number. The cesium-137 source, as we said, 0.67, almost 0.7 mega electron volts. All the gamma rays come with this energy, but as they undergo Compton scattering, they begin to lose their energy, so they go back in here. But for instance, if you have an atomic number that has 80, a value, you will see that almost immediately, the most dominant interaction that they will have will be by way of photoelectric factor. But if you go to light elements, you're going to see that it takes a wider range of energy before they enter the threshold to photoelectric factor. Of course, if the energy is high, then you can reach the per production. But what this plot tells us is that the higher the atomic number of the element being hit by the gamma rays, the faster the gamma rays undergo photoelectric interactions. And the lighter the element is, the more time, the more interactions that it will take in the form of Compton scattering before the gamma rays reach the threshold to photoelectric effect. Good. Now, when you have porous media and you have a gamma ray being sent to porous media like this, then of course some of the gamma rays are going to hit the solids, and some of them are going to hit the fluids. And that's actually the reason why we can measure the density. And of course, when the gamma rays are hitting more and more of the solids, they are closer, the faster are going to get into the photoelectric range. But the more and more they hit the lighter elements, the fluids, then the less energy they are going to lose, and potentially they can go on for longer distances, losing their energy in the form of Compton scattering. Now, there's something really interesting. What we measure this decay of gamma ray counts in rocks is essentially, as I showed you before, an exponential. They follow an exponential equation where the exponent is the electron density. So it turns out that there's a very important equation that governs the relationship between electron density and the density of the rock. And that is equation where C is atomic number and A is atomic mass. And so it turns out that for most of the minerals that we have in the earth, the ones that we deal with in our business, that relationship is approximately 1/2, whereby the electron density is very, very close to being equal to the density of the rock. But, sometimes that's the case, but there are also some calibrations or corrections, empirical corrections that produce a linear relationship between the electron density and the density of the rock. So what happens is that we measure with these count rates, what we really measure is the electron density, and the electron density is transformed to the density of the rock by way of these equations. And that's what I said about this transformation, that when the count rates are measured by the tool, those count rates are immediately converted to bulk density. And that's how this transformation works with the tool. Count rates, number of photons per unit time. There are two gates for low energy and high energy. The high energy, which is Compton scattering, is those are the gamma rays that are used for the calculation of electron density, and those count rays are immediately transformed into bulk density. And here's a plot, an interesting table that shows that for a multitude of minerals that we have in the subsurface here, represented here, the relationship between atomic number and mass, if you look at this, atomic mass is very close to 0.5. And then the value density is such, and the electron density. This is just to indicate how the transformation is made. Now, the count rates that are considered to be in the photoelectric range when they reach the sodium iodine detector, those are the low energy, those are the ones, the count rates, that are used to approximate what we call the photoelectric capture cross-section or photoelectric absorption cross-section. And that is a fundamental property of materials. And those count rates are converted to what we call the photoelectric factor. The units of this factor are barns per electron. I don't expect you to memorize that, but suffices to know is that for most minerals that we deal with in the earth, this number oscillates between 0 or let's say 1 and 5 at most. But there are some exceptions to the rule, particularly so if you have barite, which is a very heavy mineral, then the photoelectric factor of that mineral will be stratospheric for all practical purposes, 267. But the photoelectric factor, or that is calculated with the count rates of photons, is very important because it has a very close relationship with the solid composition of the rock. It turns out that it has a very low sensitivity to the fluids that you have in the rock, so it mostly senses or is sensitive to the solid composition of the rock, whereas the Compton scattering count rates of photons that reach the sensors, those are sensing everything, the light fluids and the heavy solids, and that's the reason why they can be used to estimate quantify the electron density of the rock, which is an average of both the solids and the fluids. So what happens with the corrections? Well, this is a very long worded slide. I put in here this slide only for reference. But I want to say that there are two sensors and there are count rates for each of the sensors. And what happens is that we use actually the two sensor counts to compensate, this is the important word, to compensate for the presence of mud cake. And that includes corrections for mud cake thickness and mud cake weight, which also include the case of standoff or presence of caliper variations. And I'm going to talk about those. There are some additional processing steps that are done to depth match the measurements, and there are also procedures to do high resolution versions of the logs. And I also want to say that the photoelectric factor count rates that are done are produced only with the near sensor. The far sensor is just too far to have reliable, statistically reliable count rates to produce a photoelectric factor. And here's a very interesting plot. So it turns out that logging companies, and this is done in many ways. Sometimes it's with lookup tables, sometimes it's done by inverse methods. Everything is done real time. At the same time you make the measurements, the corrections are made. But here is a very important thing that I want to mention. So this plot shows the near detector, short spacing detector, count rate. And here is the count rate for the long detector. So it turns out that if you have a beautiful rock, very engaged borehole, sensor is pressed against, sensor and source are pressed against the borehole wall, touching them nicely. All the gamma rays went directly into the formation. They came back, no mud cake. Then we have these calibrations charts that essentially they tell us, okay, so if your count rate of the near sensor is this, and your count rate of the far sensor is here, that's the electron density, that's the bulk density that you expect of the rock, and that's the value that is reported. But let's say that you had mud cake, and depending on the thickness of mud cake and depending on the weight of mud cake, what's going to happen is that your measurement, instead of falling over a calibration guide, is going to fall somewhere outside, let's say here or maybe here. And then what happened? Why isn't that measurement on the guide, the calibration guide? Well, the answer is because this is not a formation, the sensors are not making proper contact with the formation, or there's some other material that is causing abnormal counts. And so the abnormality of the counts is going to be in some case because you have standoff, in some case because you have light mud cake. But essentially what logging companies do is they have these correction charts that say, okay, so if you're here, you are here because you have mud cake, and the mud cake has a certain thickness and a certain weight. So what I'm going to do is, because I have these two sensors and I have the ability to correct for that, I'm going to bring you back to the guide. So there's a correction that is applied. So we recognize what the mud cake thickness and the mud cake weight is. And these are the spine and ribs. They look like ribs, people say, I don't know. But the point is that they make the correction and they bring the point back. And that difference between the density that it will be obtained without correction and the corrected one is what gives rise to what is called the delta rho. This is the density correction that is applied to the measurement real time because of inferred presence of mud cake with a given weight and a given thickness. So, and those are inferred from charts, calibration charts, lookup tables, a number of things, and immediately the count rates that do not match the guides are corrected. They are forced to go to the guide. That's the density that is reported by the logging companies. Want you to know that there was a correction, and they want to tell you what size of a correction was made. And it's important to know because if the size of the correction is very large compared to the density itself, percent-wise, then you know that a large portion of the measurement will be correction. So it's very important to know how much of a correction was made. And because of that, the logging companies report that correction in the form of the delta density log. This is the log, HDRA, but different logging companies have different names for this. But please note that this is in grams per cubic centimeter. Look at the values, could be negative or they could be positive because you can have corrections one way or another one. If I go back to this table, you're going to see that sometimes the correction might start from here back to the guide. So that means that the correction is negative. If it goes up, then the correction is positive. So it really depends on what type of situation you have that causes the correction to be plus or negative. But in essence, what we want to verify is that the correction is zero. That means that there was no correction made to the density measurement. If we see that some of these corrections are oscillating wildly in the left or right direction with respect to the zero, then we have to worry about it. But this constitutes essentially another quality control log that is widely used to assess the reliability of the density measurements. So it's important to know how much of a correction because the mud cake was done to your measurements, and that is reported here. Good. Now, let's go into the world of neutron logs now. Again, this is a whole different way of looking at the properties, but it's very important. Remember that when we have a rock like this is a piece of rock right here. We don't have the luxury of looking at it. We don't have the luxury of smelling it. Do you have oil? Interrogating it. Can you imagine going into the borehole and say, okay, what are you? I'm a Samsung. Well, okay, so good. What is your porosity? 20%. Or what is your permeability? 40 millidarcies. Well, we don't have that, right? So we don't have the luxury. So the only thing we can do when we go to the borehole in the absence of what I call a borehole naut, like an Uber or a Tesla car that is driven by itself, self-driving vehicles. We don't have that sort of thing. So here we have measurements, and what we do is we bombard these rock with all kinds of physics. We send gamma rays. That's what the density PEF measurements are. We bombard the rock with gamma rays. Sometimes sonic logs, what they do is they send acoustic waves, elastic waves into the rock, and then we measure the times of flights, and those are indirectly used to assess the properties of the rock. The other one is the resistivity measurement. We measure the electrical resistivity of the rock, and then from the electrical resistivity we assess, in combination with porosity, we assess the saturation of hydrocarbons, or we measure the natural gamma rays. You see, what we're doing is interrogating the rock with lots of physics, as many physics measurements as we can, so that all all combined, as many as we can, will give us the description of the rock for storage and flow. And one of those is neutron logs. And why are neutron logs used in our business? Essentially because we want to measure the hydrogen index of the formation. That is to say, how many hydrogen atoms per unit volume does the formation have? And why do we do that? This is the source. Is the reason why neutron logs became very popular is because resistivity logs cannot differentiate between oil and gas. Resistivity logs only sense the volume of electrically conductive water that we have in the rock, and the rest they don't care. It could be oil, it could be CO2, it could be gas, it could be condensate. No way to know. But all of those gas, condensate, light oil, heavy oil, they have different hydrogen indexes. Of course, CO2 doesn't have a hydrogen index, so there's no way to sense it. But as soon as you have hydrogen, then we can use neutrons to sense indirectly the hydrogen index of the formation. And this principle comes a long way. It was Enrico Fermi, the famous Italian nuclear physicist, who came up with this idea of using thermal neutrons to infer hydrogen indices. Of course, they were using it for some other purposes. There's a very, very interesting, colorful story about one of Enrico Fermi's students. His name is Bruno Pontecorvo. You can Google him. It turns out that Bruno Pontecorvo came to the U.S. It's a long story, but I'm going to make it very short. He came to the U.S., emigrated to the U.S. from Europe, and then he got a hold, or somebody got a hold of him, or he got a hold of a small logging company. They were trying to build a neutron logging tool because they wanted to differentiate between oil and gas, for instance. And so they were looking for a person who had mastery of these concepts. And the long story, Bruno Pontecorvo was recommended, and he's the one who did most of the initial. He laid the groundwork of these measurements. But there's a very interesting story about him because subsequently he began to work on other things, Manhattan Project, and then, fortunately, he defected. He defected and went to the Soviet Union, where he died. So now, he was admired in the Soviet Union. So lots of interesting stories. So I don't have time to go through all of that, but if you have a chance, I can give you the story. Is a very colorful, interesting story about Bruno Pontecorvo. But suffice it to say that because of Enrico Fermi, Bruno Pontecorvo, the idea was that we could use a neutron-based tool to detect variations in the hydrogen index of the rock, which could be tied to the fluids themselves. It turns out that that's what neutron tools do. They try to look at, understand, sense the hydrogen index of the fluids that we have in the rock, except that some rocks have also hydrogen in their matrix composition, such as shales, in the form of hydroxyls, OH radicals. So there are some complications with that matter. Subsequently, in another lecture, I'm going to show you that magnetic resonance, nuclear magnetic resonance, is another tool, different principle, that looks at the hydrogen in the rock. But this time, magnetic resonance only looks at the hydrogen that we have in the fluids. More about that. But let's begin with the discussion of wireline thermal neutron tools. So here it goes. Here is how the tool looks like. There are certain kinds of sources, but the source of neutrons, essentially what we're going to do is we are going to bombard the formation with neutrons. And there are different ways of releasing those neutrons. One is a chemical way, which is a source made of americium and beryllium. There's another way, I'm going to talk about that later. But the energy of these neutrons that are released by this chemical source is 4.5 mega electron volts. At that rate, there's a release of 40 million neutrons per second. How about that? And the strength is 20 curies. And the tool has two sensors, near and far. And now maybe you can guess why we have two sensors, right? To compensate. And we have to compensate for a few things. But one sensor is not enough for compensation. We need two sensors. So just like we had the density tool for compensation of presence of mud cake. Okay, here. The sensors are made of, they're helium detectors. It's a very interesting principle as to how helium detectors work to detect neutrons. It's a nuclear reaction. So here's a tool. The tool uses a bow to press the tool against the borehole wall as an extension bow. The sensors are behind this sleeve. And here's where the source is inserted. That's the magnesium beryllium. And this is the insertion device. That's how it looks like, size-wise. Now, another way to send neutrons to the formation is with the so-called minitron, which is a pulse neutron source. Essentially, we use ions that are sent through a magnet at high energy and they are bounced off to a target, and that bouncing off a target releases neutrons. And those neutrons have an energy of 14.4 mega electron volts. Compare that energy to the energy of 4.5 mega electron volts that comes from the chemical source. So it's almost 3 times. Now, with more energy, you can do more things. It's just as, for instance, one of the most important applications of neutron sources is that they can go through casing. You see, not many measurements can go through steel casing, such as resistivity. So with neutrons, the more energy, the easier they will go through the rock casing, and also the longer distances they can take before they are absorbed by the medium. And then in this case, we have about 100 million neutrons per second, so a higher count. So those are the two possibilities. So in the industry, we have the two sources, the chemical source and the pulse neutron source. The pulse neutron source is not only higher energy, but also is, as the name says, pulse. It's easier to control because you can send pulses of neutron. In the case of the chemical source, the neutrons are being sent all the time. It's like continuously. Whereas with the pulse neutron source, you can send pulses at a certain regular interval. So you have more control, and because of that control, you can control and do better interpretations. So here, what are the ways in which neutrons interact with rocks, with porous media? Well, there are three types of interactions. And the interactions, again, depend on the energy of the incoming neutron. And I just told you what the energy is for the different sources. But let's say that you have a high energy neutron and it comes here and impacts a nucleus here. What happens, this is like a collision of two billiard balls that we play. So this is a conservation of kinetic moment and everything else. But essentially, if the neutron has high energy, some of that energy is going to be given to the target atom. And when the neutron bounces off, it will bounce off with less energy because some of the energy was transferred to the target atom. So it turns out that the loss of energy, this is the interesting thing, the loss of energy will be higher. The loss of energy of the incoming neutron will be higher as the atom becomes closer and closer to the mass of the neutron. And that's hydrogen. You see, hydrogen has a very close mass to that of neutron. So when you have a hydrogen atom in collision, the neutron collides with the hydrogen, but when it finishes the collision, it ends up with the least possible energy because the rest of the energy was transferred to hydrogen. If it hits a very large atom, then the loss of energy will not be as high. The loss of energy by the neutron will not be as high as that when it hit hydrogen. The other thing that happens is when these inelastic collisions happen, there's also emission of gamma rays that are used for other purposes such as CO2 activation, carbon oxygen activation, that sort of thing. And then when that happens, we reach another state in which lower energy. In that case, the only thing that happens is no longer the emission of gamma rays. The neutron continues to bounce off atoms. Every time it bounces off, it loses energy, and the loss of energy is higher when it hits an atom of equal mass, in this case hydrogen. We call that elastic in scattering. So it's elastic, and the first one is inelastic when we have these inelastic gamma rays that are being released. And last but not least, the thing that happens is this. After a long period of time when the neutrons are losing energy after sustained collisions, one after the other, they lose energy, then suddenly they become what we call thermal neutrons. They diffuse, and they're very slow. And because of that, when they hit an atom, they, instead of being bounced off, when they have reached this thermal threshold, then instead of being bounced off that atom, the atom captures them like a Pac-Man, captures them, and they're gone. One less neutron. This is how the neutron count decreases. It's because they continue to lose energy until they are captured, so one less. And that capture will give rise to a gamma ray. And those gamma rays, well, essentially the capture of the neutron by the atom will make the atom that captured the neutron, it will make it unstable, radioactive. And because it becomes radioactive, now it begins to release gamma rays. And the energy of the gamma rays that are released is directly connected with the atom that gave them. So if we have a sensor to sense these gamma rays, and the energy of those gamma rays, then we can indirectly understand, quantify the types of atoms that originated them. And this is a principle of another tool that I'm not going to talk about there. Now, I also want to say that chlorine, there are several elements that love to capture thermal neutrons, and one of those is chlorine. So, and there are others, we call this thermal neutron capture cross-section, but chlorine is one of those that has a very high one. So you have salty water, and of course salty water has chlorine, then the capture of neutrons is accelerated, and this principle is widely used for another measurement that we call thermal neutron capture cross-section, or sigma, but I'm not going to talk about that. Also as measurement that you can do through casing. Good. So what is the principle? The principle of this neutron source is very simple, that we have a neutron source that sends a certain number of neutrons. And then those neutrons are going to undergo all of those three interactions: inelastic, elastic, thermal capture. Bottom line is that the longer the distance, more of them are going to be captured in the medium. So if you have a sensor over here, the count rates that you are going to be will be obviously lower than at the source because, number one, geometrical reasons, distance reasons, and also if you have a medium that has lots of neutron absorbers such as chlorine or hydrogen that causes the elastic collisions to lose energy very fast, then the count rate is going to decrease. So what we do is, and this is the principle that we had with Bruno Pontecorvo, before he defected, and before he went to the Manhattan Project, is that we know that if we can control or infer the number of neutrons that go here, and we count how many make it to the sensor, then that can give us an idea of the hydrogen index of this formation, or even presence of chlorine, for instance, absorbers. But that is all controlled by what we call the mean free path of these thermal neutrons, and the distance is here. And the mean free path is a function of many things, but essentially hydrogen index, presence of chlorine, and other things. So that's what neutrons do. And when you have gas, for instance, compared to water, what happens is that the hydrogen index of gas is lower than the hydrogen index of water. And because of that, you have fewer hydrogen atoms per unit volume. And consequently, if this brown substance here is gas, what will happen is that some of them will be absorbing here because of the hydrogen in gas, but because the hydrogen index is low, many more neutrons will make it to the sensor here than in the case of water, because water has a larger hydrogen index compared to gas. And then, so the count rate of thermal neutrons will be lower in the case of water than in the case of gas. You see, those differences are what allow us to infer indirectly the hydrogen index of the formation from the differences in count rates. Clear? So here's a diagram that just shows a busy day in the life of a neutron. So when a neutron goes, it goes out with high energy, and then it goes and loses energy. It goes from epithermal, inelastic, goes to collisions, loses energy, more emissions of gamma rays at the beginning, inelastic gamma rays at the end. These are captured gamma rays, but in between it's the hydrogen index of the formation that gives rise to the loss of energy, and the capture is accelerated by the presence of elements such as chlorine and boron that have a high capture cross-section. But in general, in our business, we have to worry about hydrogen because that's for elastic scattering, loss of energy, and chlorine because of the ability to absorb thermal neutrons. Those are the two things that we understand, hydrogen and chlorine. Now, here's a picture of what happens. So when you begin, your energy, your source sends your neutrons. Then the neutrons begin to interact with atoms. The interaction of the atoms will give rise to loss of energy. And so they go and interact with another atom, more loss of energy. But essentially, at some point, the loss of energy will signify that they become in the so-called thermal regime. And when they go in the thermal regime, they're captured. And when they're captured, they release a gamma ray. And the gamma ray is now interacting in the form of Compton scattering, just like in the density tool. So we can actually look at these gamma rays, their energies. And from the energies spectrum that they have, we can infer back what is the chemical composition of the atoms that capture the neutron. It's like reverse engineering in the atomic world. How about that? And we can look at those gamma rays, just like we do for the density source. And that provides actually another way to estimate density, but I'm not going to talk about that today. And here is a plot of the tool itself. Here is the source. That's the bow that I showed you before. Here is the near detector, and here is the far detector. And what happens is that neutrons, in this case, they cannot be collimated. So when neutrons come out here, they go everywhere, especially in the for the two sources, for the chemical and the minitron source. And look at the cloud of neutrons as at a given time. Essentially, those neutrons are going to go everywhere. In the picture that we had of the density tool, because they are collimated, we can concentrate them on one side of the formation. But here, no, they go everywhere. It's like a spherical expansion of the cloud. But some of them are going to make it back to the sensor, and some of them are going to make it back to the near and far. Unfortunately, some of those neutrons are going to make it through the back end, that is to say through the borehole instead of the formation. And because some of them are going to make it through the borehole, the mud composition will play a very, very important role into the count rates. So it turns out that neutron tools, they're excellent because they can signal differences between hydrogen index of rocks. Good, that's good. That allows us to differentiate between gas and water saturated formations. But on the other hand, if you have a large borehole, you have a borehole with lots of hydrogen and you have a borehole with lots of chlorine, then all of those things are going to accelerate the capture of neutrons, not the formation. So we have to make corrections. So here's the thing, neutron tools require a heavy amount of corrections, and unfortunately those corrections are very drastic sometimes, but they need to be made. So every time that you use a neutron instrument, please verify that all of those environmental corrections were properly applied, because if not, your measurement could be substantially affected by this. And here is a picture of where the source is located, and so that you know. Okay, now here's another cartoon that shows here's the initial energy of the sources, either chemical or pulse neutron electronic source. The point is this, that the energy of those neutrons is going to decrease as a function of time and distance. If you have lots of hydrogen, the decay is going to be very fast. If you have lower amounts of hydrogen, smaller amounts of hydrogen, the decay is going to be relatively slower. Eventually, all of the neutrons will be captured, but the rate with which this will happen will depend on the concentration of hydrogen and the concentration of chlorine. And that's what we look at, that if we can understand how many the capture, how many neutrons are captured, and compare them and calibrate them, that can give us an indication of the hydrogen index of the formation. And we do that in the field with this principle that these calibrations are actually performed not from the differences between the count rates of neutrons sensed by the near and far detector, but by the ratios. So here we have the near, this is the neutron tool right here, it's a cartoon. We have the source somewhere here, and then we have the near detector and the far detector. So we know that as we go far away, the count rate of neutrons decreases, but also the material that they went through will have an impact on the decrease of neutrons. But rather than looking separately at the count rates, what we do, and this is something that was discovered by all of these bright astrophysicists that work with logging companies to make these measurements useful, is that they calibrate based on their ratios. So rather than taking the differences, they take the ratio between the count in the near detector over the count on the far detector. And of course, because the near detector is closer to the source, we are naturally going to measure more count rates of neutrons than the far detector. So we just count how many neutrons make it to the near sensor, and we count how many neutrons make it to the near sensor per unit time. We capture them over the same time window, and we take the ratio. And that ratio is what is used to calibrate rock porosity. So we take this count rate. What is your count rate real time? So this is my count rate. So we bounce this off through the calibration chart, and that gives us the corresponding water field porosity. Now, we have a choice. These calibration charts, these count ratio calibration charts could be done for one for quartz, one for limestone, and one for dolomite. Now, you can ask me, why are there only 3 standards? Well, that has to do with the origin of who did this. Apparently, these bright astrophysicists who work on this principle did not know that there were more types of rocks, and they found that maybe by doing 3 main calibrations, they could cover all the cases, and the main calibrations that they used were quartz, limestone, or dolomite. So essentially, when you're running the tool in the borehole measures the count rates of neutrons reaching the far and near detectors separately. Then they do corrections for depth matching and so forth. They take the ratios, and the ratios are converted to apparent porosities. The apparent porosities are calibrated assuming that the fluid is fresh water. This is a very important assumption. Now, and the logging tool asks you, what do you want me to give you the apparent neutron porosity units? In limestone, dolomite, or quartz? Okay, well, choose one and we'll give you. But that's not a problem because you can always go back from one or the other. So you have different calibration charts for each one of those. And those calibration charts are also a function of the tool itself. Even Schlumberger for logging while drilling, they have a calibration chart. For wireline, they have a calibration chart. For Baker Hughes has one. Hildebrand has another one. So it varies according to the type of tool. So they use those, and those charts are fed into the computer when they're logging. So real time, they're giving you these results. Okay, but the important thing is that we use the ratio method. And the calibrations that I was talking about here, of course, you give me the ratio that you have, you bounce this off any of this, and then it gives you the corresponding porosity units, assuming that you have water. And that's the origin of these apparent water porosity units. When you have gas instead of water, so it turns out that the ratio will increase considerably because you have fewer hydrogen index. So the porosity will tend to be the opposite way. When you have lots of gas in the formation, the hydrogen index will be very high, so the ratio will be low. So in consequence, when you convert it back to equivalent porosity, it will give you very low porosities. And that's the reason why when we have gas saturated formations with high porosity, the neutron porosity appears as abnormally low, and it's because we're using the standard of water to calibrate the porosities. So that's what I've been saying from when we started to introduce these measurements. All right. But as I said before, neutron logs are very important because they are the ones that give us some indication of fluids that are lighter than water because of their hydrogen index. But because of the presence of the borehole, and because of the fact that the cloud of neutrons goes everywhere, is not a collimated cloud, then they are also affected by borehole conditions. Of course, there are many conditions in the formation that affect neutrons, and those are temperature, pressure. The good ones are matrix, porosity, water salinity, presence of chlorine. Okay, but borehole conditions, borehole size, borehole shape, mud cake weight, thickness, tool standoff, separation of the tool with respect to borehole wall, and then the kind of mud, the weight, the types of solids, whether the solids have any hydrogen or chlorine, the fluid type, whether it's OBM, it has a hydrogen index, whether it's water-based, the salinity, the temperature, and the pressure. All of these corrections, many of them, have to be applied to the neutron logs. Of the different logs that we work with, probably the neutron log is the one that is subject to the most borehole environmental corrections, and those corrections could be large, so we have to be careful that they were applied. And some people, to the extent that some people don't like neutron logs because of that, because of the multitude of corrections, but they're useful. I think some of these corrections are extremely reliable. We just have to be aware of whether they were made and so forth, so on. But never ever interpret neutron logs if you're not sure that all of these environmental corrections were applied to them. Otherwise, you're going to end up with the wrong assessments. And I mentioned something about the concept of apparent neutron porosity. This is a very long slide, so I'm just going to fly through it. You can read it. But it's about how count rates are transformed to artificial blocks, and solid composition, the influence of fresh water, the compensations, the ratios between near and far, and also all of these measurements are delivered assuming that you have a borehole of 8.5 inches filled with fresh water, and the count rates are depth match, some details that are important. Okay, now let me give you some practical engineering considerations about these measurements, which you should remember when you interpret them. Number one, the tools are laid out like this. This is the Schlumberger tool, but let me just mention. The tool string is very long, but the litho density tool has, this is the density measurement right here. this arm is the caliper we use for the caliper. Press against the borehole wall. This measures for electric factor and density. Then over here we have the neutron tool on top. We have a spacer here or a cartridge, but this is a neutron tool. And at the top here we have the gamma ray tool, which could be the standard gamma ray or the spectral gamma ray. But it's important that they are not operating at the same depth. So we have to depth match the measurements subsequently. But that's important because we don't want interference. That's one thing. The second one that I want to say is that the energies of the gamma rays from the cesium-137 or coming from the Minitron tool will have nothing to do with spectral gamma ray logs. These spectral gamma ray logs, their energies are so low compared to the energies that we deal with for the cesium-137 source that they're almost negligible. So don't worry about these gamma rays. And also the sensor is different, it's larger, and the count rates coming from these elements are much lower compared to the count rates coming from the cesium source. So even though they're there, they are marginally impacting the measurement. I want to say that. The other thing that I want to say is that all of these tools, neutron, density for electric factor, they are all calibrated using artificial blocks. There are many places where these calibrations take place, but it's very important that they be calibrated because of differences in tool size, the armor, the shielding, all of those things. But essentially they need to be calibrated properly. The other thing that I want to mention is that these tools are pressed against a borehole wall. The density is a bad tool. The neutron is not, but it's pressed against the borehole wall with this bow. But in essence, what happens is this. If you run the tool, that's a density tool, through a section of the borehole where the borehole size is not engaged, is not uniform, then the tool, the pad, is not going to make proper contact with the formation. You see that? We have the source right here. That's the source at the top, and these are the near sensor, and this is the far sensor. And if the three sensors that are in the pad are not engaged, properly engaged with the borehole wall, then you are going to be sensing something in the fluid, not in the formation. And that's important depending on where you are. As the tool moves, you're going to see that it moves at different places. So we are going to sense different things unless the tool is properly engaged. Similarly with the neutron tool. So that's an important thing to remember. The other thing that I want to mention is that because of the size of the pad and also because of the size of the tool, density logs have probably the highest resolution possible beyond the one that one can achieve with borehole imaging tools. And neutron is a little bit less resolution, 30 centimeters versus 20 centimeters in most cases. Of course, this will vary across whether you have wireline or LWD, but it's important to know compared to other instruments so that you have an indication of how well one can sense these properties. And that's important also because the density log is by far the highest resolution log that we have of all the different ones. And because of that, it's also extremely sensitive to caliper variations. All right, and that's important to know when you go to formations of this kind where layers, the thickness of the layers is varying between sandstones and shells, and because of that, we are making averages of the tool properties when we measure them. So these are no longer homogeneous properties. Now, when you go through bed boundaries or when you are in the center of very thin beds, the average is not only sensing that bed, but the beds are adjacent to them, and we call that the shoulder bed effect. Okay, now let's look at some examples. What I propose is that after this, I hope you didn't fall asleep. I know it was a lot of theory, it was a lot of talking, but this is where things become very interesting because now we're going to apply what I talked about, and we're going to apply them to do two things: to analyze the types of solids and to analyze the types of fluids, the effect that solids and fluids have on the charts. And from those effects, we're going to be able to assess dominant solid composition, and from those effects, we're going to be able to estimate the porosity of the rock. I'm going to show you some examples of clastics saturated with water, some clastics saturated with hydrocarbon gas. I'm going to show you some cases when we have shales, what the effect of the shales is. I'm also going to show you some cases where we have caliper problems. I'm going to show you several cases where we have mixed lithologies, such as anhydrides, carbonates, clastics in the same sequence. I'm also going to show you some interesting examples of carbonates and mixed sequences. And we're going to conclude with some examples for the analysis of the dominant clay mineral composition by combining PEF measurements with spectral gamma ray logs. So several examples. So before we go there, I suggest that you take a break right now. Go take a snack, take it easy, reset the mind, go back to maybe read more of the book by Darwin, my friend Darwin Ellis. I hope you like Darwin, that I'm here supporting your book. And read it, understand it, think about what I said, shoot me emails, ask me questions. I hope everything is understood. I hope you understood the principles. Let's take a break, cup of tea, 3 cups of tea, coffee, whatever helps you, and let's come back in a few minutes to go through the examples. Okay.